All right. I'm going to take it off in just 1 second. Okay, so factorials. If you guys notice, there's an exclamation point, and it has a mathematical meaning. So let me show you a few factorials. 0 is the tricky one, kind of like something okay. Shh. Do you guys remember anything to the 0 power is 1? You kind of had to memorize that. Now maybe some teacher once along the way showed you something cool, like, well, if you have 5 over 5 to the 5 and 5 to the 5, we know those are the same and they equal 1, but exponent rules, it's 5 to the 5 minus 5, which is 5 to the 0. Therefore, anything to the 0 is always 1. There's like a reason why. Yeah, there you go. But this is another, basically, we kind of just have to memorize. But some of you are like, I don't even know what factorials are. Okay, 1 factorial is just, well, look at a factorial. A factorial says start at 1 and go up to n. Well, guys, is there any up to do for 1 factorial? No, so it's just going to be 1. But 2 factorial would be 1 times 2. 3 factorial would be 1 times 2 times 3. So that would be 2. That would be 6. 4 factorial would be, wait a minute, hold on. We could do 1 times 2 times... Okay, did you guys all get that? Joe, pause and let them think. So then couldn't we say this is 3 factorial times 4, which is 24, which is why Jason was saying 24 real fast. He's like, oh, times 4. And then 5 factorial, wouldn't we just go 1 more? So we would say 120, and we could keep on going and keep on going and keep on going. So if you see some sort of number or some sort of letter with an exclamation point, I mean, if you want to be really enthusiastic, it could be like 3, and that's totally great, but it has a meaning. It means 1 times 2 times 3 is 6. That's actually kind of funny. Although, Joe, I'm not sure if the louder you shout, the bigger it gets, because 1 shout would make it bigger, and then you're done. So in some ways, yes. In some ways, no. Now, with letters, it's going to get a little bit more complicated. Because with letters, it's going to be like, Okay. 2n factorial versus 2n factorial. Wait, I just said the same thing. So pay attention. 2n factorial and 2n factorial, they are different. This one is saying the quantity 2n, the factorial of the quantity 2n. This one is saying 2 times n factorial. If I was to ask you which one was bigger before revealing what they actually are, I'm not sure what you guys would have said. If you understood factorials really, really well, and if you're looking at them right now, hopefully you say the bottom, because this one's going to go up to n and keep on going. Twice as long, twice as far. So if, for instance, n was 10 times 10 factorial, oh, that's huge. Well, no, it's actually just 1 through 10 and then times 2. 2n factorial is 20 factorial, which is 1 through 10 and then keep going to 20. It's going to be not just times 2, but times 11 and 12 and 13 and 14 and 15 and 16 and 17. Way stronger. Way stronger. Because this one is 2 times 1 through n. This one would be 1 through n, and then a whole lot farther. Now, why am I trying to show you how variables with factorials work? Because what if they say find the first 5 terms of this sequence and all of a sudden there's a factorial? A1, A2, A3. Now this is a nice, not recursive, but nth term formula where we just have to plug and chug. N is 1, N is 2, N is all the way up to 5. Okay? But when we plug and chug, well, we just have to know how things work. My question to you in some way, shape, or form is which one you think is stronger, 2 to the power of n, exponential growth. Swoop, there it is. Whoa, the fastest one we've seen so far this year. But on the bottom, now there's this new factorial dude. Is he stronger? Is he weaker? Let's see if we can find a pattern. So this guy, 2 to the power of 1 all over 1 factorial. Okay, top wins. He's stronger, 2 over 1. Okay. But 2, now I have 2 squared. Bless you. All over 2 factorial. Well, I have 4 over 2. Okay, the top is still stronger. The squaring made more of a difference than going up 1 in the factorial. You guys help me out. What's the third term? 2 cubed all over 3 factorial. So now I have 8 over 6. Good. 1 times 2 times 3. Which is 4 thirds. Uh-oh. think the bottom's catching up. How about 4? 2 to the power of 4 times 2 times 2 times 2. Like, okay, this is getting bigger. But isn't 8 times 2 just 16? And what's 6 times 4? Oh, the bottom's overtaking the top. Divide both by what? 4? Oh, by 8. I get 2/3. Bless you. And what if I plug in 5? 2 to the power of 5. That's huge. Oh, don't worry, though. It's just 16 times 2. And now it's 5 factorial. 24 times 5 is... Oh, man, the bottom's getting way bigger. At least bigger faster. 8. 4 goes in. I guess we can go one more. 2 goes in, 4 over 15. Now, guys, this is one. The pattern would be super hard for you guys to pull out, like from your minds, because it's not super obvious. I mean, it was 2 and then 2 again, and then 4/3 and 2/3 and 4/15. Like, the pattern's not obvious, but it does come from the formula. But what I also wanted you to see, oh, wait, we were supposed to start with 0? Okay, if they tell us to start with 0, we start with 0. No big deal. But what's anything to the 0 power? And what's 0 factorial? We have to memorize that, but also 1. But anyway, I also wanted to show you factorials. They're actually the fastest type of growth. Now, guys, we could play around with factorials, and maybe that's a good thing, and maybe we'll get back to that. But actually, there's something else we got to talk about, which are series. So let's play around with just a couple factorials. I have about 10 minutes left. Let's play around with just a few factorials. I might not have you play around with all of them. Maybe just a couple, and then we'll go do the variable one because he's harder. But then we have to go talk about series just for a little bit. So, 8 factorial. I have to go ahead and multiply, multiply, multiply. Or, couldn't I say that 8 factorial, guys, doesn't it just go all the way up to 8? But who also goes up to 5? Aren't some of these going to just reduce? So couldn't I have just rewritten this as 1 through 5, and then it's a few more? See it? If I don't have to write out everybody, I can be like, oh, hey, whoever's the bigger factorial, you're going to include the lower one and just have a few more. So now I just have 42 times 8, or 56 times 6. I like that one better. That would be 336. Is that right? 56? 6 and 3? 330. But what about this guy? What do you guys would think would be a strategic way to attack this guy? 1 times 2, 1 times 2 times 3. Well, hold on, wait. But didn't I just say the biggest factorial will include the others? So couldn't I rewrite, well, if I'm going to try to cancel out, why not go for the big guy, right? So can't I say, what is 5 factorial? 3 factorial times 4 times 5. The 3 factorials can cancel, and I have my 1 times 2. Oh, can't I reduce? 2 and 4 is 1 and 2, and so the final answer is. And I didn't have to do 120 over 2 times 6, which is 12, and 120 over 12 is 10. Like, I could have gotten there, but if the numbers get bigger, it's going to get harder and harder. So the more you can simplify, the better. So let's just do one last one. I want you guys to tackle this guy. One last one with numbers, then we'll go see one with letters. We're going to go ahead for sake of time. We're going to skip that one. I can only give you a couple seconds, but try to tackle it. There are different ways, but you're trying to do as little mental math as possible, aka you're trying to simplify out as much as possible. Anybody get 14? How did I do that in my head? Did I literally do 8 factorial over 4 factorial over 5 factorial? Heck no, techno. What do you think I got rid of in my head first? Uh-huh. And how did you rewrite 8? 5 times?
6 times 7.
What was able to happen to the 5 factorial then? And then I was like, well, the 1 doesn't really make a difference. 2 times 3 times 4. 2 times 4 is? Or we could do 2 times 3 is 6. But I got rid of the 8 with 2 and 4. And then doesn't the 3 and the 6 just reduce to 2? And 2 times 7 is? But how much harder would 8 factorial all over 4 factorial 5? Oh. Okay, would have taken some time. Now, guys, that's not to say that all of these are always this easy. Like, sometimes the top is a lot stronger, so there's a lot more numbers that we have to deal with. It's not always this easy. But just showing you the idea that we're skipping this one for sake of time. With factorial expressions, since they all build up from 1, there are definitely things that can reduce. So now we have to figure out, how do we apply that to variables? Oh, who's stronger? N or n minus 2? Good, the bottom. Because the bottom says, let's go from 1. Oh, I don't know what n is. Is it 10? Is it 100? I'm going to actually put n over here, and you guys will see why in a second. But 1 through n. How high does this guy go? 2 less. What would go after n minus 2? Have you guys noticed it's always 1 higher than the one before it? Or if we go backwards, it's always 1 lower. These always count by 1s. What would have been next? N minus 1. And what would have been next? So check it. This one goes all the way to n, which means he's there and he's, oh, look. All of that goes away. When I reduce, there's a 1 left, and I end up with 1 over n minus 1 times n. 2 factorial expressions in a fraction ended up actually being a non-factorial answer. Interesting. Okay, I said we had to get to series. So here we are. Pause. I'm going to put some parentheses around things I don't need you to write down. Okay? I'm going to put some parentheses around things I don't need you to write down. Even though it would be good, I don't need you to write down all those properties. What I do need you to write down is that a series is a sum of a sequence. Sequence A1, A2, A3, A4 separated by commas. Series A1, A2, A3, A4 combined with addition. Now, if you are, or when you start practicing for your SAT, studying for your SAT with Mr. Che or Elite Math or something else, you're probably going to have to talk about this little guy called a sigma. Oh, wait, we already talked about the Greek letter sigma earlier this year. But he's also called a sigma notation for summation. It's a summation. I can take this big, long, repeated addition and summarize it in this little baby notation. What that means is if you were to be given an example, like over here, the sum from 1 to 5 of 3i, I is just a little variable, in essence, that we plug into. So we would actually plug in 1, because that's the lower bound, and we would keep plugging in by, we're going from the ends 1 to 5. So 3 plugging in 1, plus 3 plugging in 2, plus 3 plugging in 3, plus 3 plugging in 4, plus 3 plugging in 5. Now, it's kind of tedious, which is why this notation is a whole lot easier. And there are some things that we could do to simplify the process just a little bit, in the sense of, what do you guys notice that every single term had? Greatest common factor would be 3. So we could have actually, at the very beginning, we could have pulled, and that's one of these properties over here. Yeah, we could have pulled the 3 out, and we could have just said 3 times 1 plus, well, sorry, my I should still be in there. Remember, repeated addition is really just multiplication. So all of this adding, I ended up having 1 plus 2 is 3, 6, 10, 15 3s. And 15 3s, well, that's 45. And the formula could change a little bit. It could get a little more complicated. And if it was a little more complicated, oh, it could even start somewhere else or have a different letter like a K. But whatever we have, we start with the lower bound. We end at the upper bound going by ends. So this one, for instance, would be 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared plus 1 plus 6 squared. Now your calculator, to be honest, in the math menu does have, as long as your calculator doesn't have a yellow button for the second instead of like a blue or a different color like a gray. Under math, if you guys go up towards the bottom, there is something called a summation, but remember, we have to be able to do things by hand also. But I want you guys to see something. Couldn't we have split this up just to be all the ones, since addition is commutative, plus all of the squareds? Could we have done that? And that shows you the property, too, that we could have split this up to be the sum of the ones. And we have a 1 for every single 3, 4, 5. We have a 1 for each of those. And then we could... So the properties kind of just naturally occur because we can take out common factors or we can rearrange addition. But either way, well, this one's going to be a little bit harder because it's going to be 16 plus 25. Hey, that is 25, and that's 50. And 36 is going to be 50, 86, and 4 is, I think, 92. But anyway, series is something else. As far as sequences and series is another way where we can have patterns between terms, but it's actually in context of all of them needing to be added together. Now we'll see when we get into section 9.2, 9.3, some different like situations where they're used and where they might come up. But you are going to have to play just a little bit in homework with these things called series. So this last page, it seems kind of crazy. It seems kind of weird because all of a sudden they said, whoa, what if there's an infinity on top? An infinity on top means what? You just keep going. It doesn't make sense. That's impossible. Just get bigger and bigger and bigger and bigger and bigger. But wait, if the sum is from 1 to infinity, now you're going to hear the third partial sum. That means just find the sum of the first 3. Third says the first 3. Partial means you're not going to infinity. Isn't that point plus 0.03 plus 0.003? What happens if we were to keep going? Wouldn't it be 0.333333333333? An infinite sum, adding and adding and adding and adding and adding can be one little set finite number? Bye, guys. See you later, Gators.